You have Discord? It's like an
Yeah, I
application.
think I did actually, yeah. Send request, yes.
Yeah, your username. I can add you right away.
I'm not sure. Jim Possible. Jim Possible, that's what I put it with.
Oh, it's like a. This one has like a hashtag.
Oh, actually, I don't.
Okay.
We'll
Well,
have to grab it next time.
Okay.
Yeah, yeah.
I have papers. Well, I also do, right? You.
Yeah, they discussed it.
It's what I thought, so they didn't come back there.
Because I put said portable in a bowl, they thought you were all poured in a can. I'm pretty sure.
And that made, instead of everything canceling nicely, and you're getting like R and one, I was getting really big values, and I was like, this is not working. Something was crazy wrong.
Yeah. Also, I'm sorry.
I was
I just realized Thursday, tea might be good.
selfishly.
Yeah, I realized that when I got.
I don't know why I was thinking, I know something, you know, some appointment for me got canceled, but some day.
Yeah,
But that's, they were closed on Monday for me.
yeah, I've been along with it, I didn't think about it till I went home.
Because it just happened, somebody was, you know, trying to cancel an appointment and they said, oh, something.
They probably just wanted to take the whole weekend off.
Yeah. So you get extra days, right? It says September 6th. But, just waiting for some more people to come. I'm just trying to see. Christmas and Green.
Christine and
Chrissy was never here. Oh, she left, right?
oh,
We only 8 people, not 10 people. Yeah, everybody's here. Right? Yeah, everybody's here. All right. What I want to do today is to get started with second order differential equations. Okay. Last time we already saw that when we solve Helmholtz equation in cylindrical coordinates, we have the Bessel differential equation. Okay. So so some of the I'm just going to list. Okay. Some common second order differential equations that we'll come across. Of course, simplest is harmonic oscillator, right? That we already know. That's your simple harmonic oscillator. Should I close that a little bit? Is it bothering? I mean, the noise? Can keep one door, one window open so that
Yeah,
there's some
yeah.
airflow, but at the same time.
Yeah, that'll be
All right. The other common equation, second order differential we are going to come across is the Legendre differential equation. Notice that this term is actually a derivative of that, okay? This is some implication, we'll talk about this much later. I mean, such differential equation they have special property, we'll exploit that much later, but just note that for a minute. your ordinary Bessel differential equation that we came across last time. Alright. And then we have Laguerre, which comes, we have associated Laguerre, but in hydrogen atom problem, but it's related to this one, so I'm going to write that down. That's Laguerre. Then Hermite, which is what we come across in, I'm going to write it on top so that you can look at it. In quantum mechanical oscillators. We come across in when we talk about quantum mechanical oscillators.
I'm assuming that's supposed to be equal to 0.
Yes, absolutely. All right? Yeah. So you can see that, some of them look very only small change, but it is, the solution will be very different. So we have to learn, basically at least these differential equations are going to come again and again in physics, right, in quantum mechanics. So, or electromagnetic Legendre differential equation come in, a lot of it in electromagnetic theory, and associated Legendre, of course, in quantum mechanics, right, when you do in spherical coordinates, in Schrodinger equation, you solve that, you get it. So we have to learn techniques how to solve these equations, what are the solutions of these differential equations. So that is a goal, right? So let's talk a little bit in generalities first to understand some of the terminologies. Okay, the equation that we saw, we call them as linear. First, the word linear. Okay, second order differential equation. So we have to understand the word linear, we have to understand the word order, okay, what we mean by that. So I'm going to write a very general nth order differential equation, which will look like this, right? So I also have to use the word homogeneous or even homogeneous. So these are the words that we have to understand the meaning of all these things, what we mean by homogeneous. The ones which we saw, the right hand side was 0, so it's homogeneous differential equation. If this was 0, right hand side is 0, yeah.
Is that a minus at the very end?
Right here, no, plus, I mean, they're all different terms. I think it got erased. It's just different. So this is not nth order. Nth order is the highest derivative appearing in your differential equation. Okay. So this is nth. What I've written is not second order, nth order differential equation. The ones which you saw it was d squared y over dx squared, so second order. So order refers to highest derivative appearing in the differential equation. And if the right hand side, if fx is equal to 0, we will call that as a homogeneous differential equation. Okay, if fx is not equal to 0, that will be inhomogeneous differential equation. Now, so we address this, we address this. Linear. Linear is, we'll only be talking about linear, we are not going to be talking about non-linear differential equation at all. It refers to the power of the highest derivative. If this was to the power of something, okay, that would be, the degree of differential equation. This is another word which is degree of differential equation. So linear means this is not raised to any power, okay? I mean, whatever it is, it's not something to the power, okay? So that's what we are going to be restricting ourselves to, linear, differential equations only, all right? And initially we'll talk about homogeneous second order differential equations. Eventually address inhomogeneous differential equation, we'll use Green's function methods. We'll come to that also. Okay, but second order inhomogeneous differential equation, we'll discuss that also. So these are the different terminologies: order, homogeneous, inhomogeneous, and then degree of the differential equation. Okay, and we'll be just restricting ourselves to linear differential equations. All right.
So it's the degree of the highest derivative. So if we have y double dot plus y dot squared, it's the linear.
It's the highest derivative, yeah, yes, exactly, yeah. It's only at the highest, yeah. If it is the other terms, it doesn't matter, yeah. Good, yeah, that's a good question. Okay, so what we are going to be doing is, as said, second order differential equations. So let us first the way most of the solutions or methods that we'll be describing, whatever the differential equation is, like Legendre, 1 minus x squared we had, right? D squared over y double prime was there. But we will write all differential equations, second order differential equation in this form. We'll make the coefficient of the second derivative of y with respect to x as 1. We'll just divide through. And we will write the homogeneous differential equations, we'll write it in this form, or any differential equation. That is, let's go back to our Legendre differential equation. What I mean by this is the following. This is my Legendre differential equation, and I need to put that in this form, okay, always to get all the methods. So what we'll do is divide through by this coefficient, which will be a2x in our general formula, right? I mean, plus L times L plus 1 divided by 1 minus x squared y equal to 0.
the second term y dash is missing.
Huh?
The second term
Y
y dash.
prime is missing.
Right.
Yeah. So, so we'll put it in this form and identify this coefficient as P of x. So P of x would be then minus 2x over 1 minus x squared. Q of x is L times L plus 1 over 1 minus x squared, right? So, I mean, you know your Bessel differential equation, x squared y double prime, what was it? Our Bessel equation, you have to divide through by x squared, okay? And whatever that you get is your px and qx. So that is, the first step is any differential equation you get, you put it first in this form, okay? So that the coefficient of this term is 1. So for Legendre Bessel differential equation, px will be 1 over x, right? Because this is what our equation was. So px, or Bessel differential equation, is simply 1 over x. Q of x is x squared minus n squared over x squared, so it is 1 minus n squared over x squared. Okay. So that will be Q of x. Why is this important? Whatever solution we are going to be proposing for second order differential equation, what we'll do is analyze the properties, analytic property of P of x and Q of x. That's the first step. Given any differential equation, first bring it in this form. Okay? And then we analyze the properties of P of x and Q of x. Okay? So so what we're going to do is, most of the time we'll be expanding about x equal to x0. And we'll first see whether at x equal to x naught, my function is well behaved. It blows up, can I do something about it and still can propose a series solution. So something like this, we can propose a solution of this form, a series solution of this form. X naught, it's any function. Any function can be, if it's well behaved, it can be expanded in some kind of series. Okay, this is that like Taylor series or whatever. It's a power series. Any well-defined function can be expanded in some kind of series. So the whole question is whether it's well behaved to write a series solution. If some of these coefficients blow up, of course we cannot propose a series solution. So that will be our starting point, and so we have to see whether we can do it or not. Okay. All right. So maybe, okay, let me just classify that. So the point x equal to x naught can be classified into different types. One is called ordinary point. Let me just say classification of the expansion part. Or singularity of x equal to x0. The point about which you are making the expansion. It could be a regular singular point. Let's say an ordinary point, first type. X naught could be an ordinary point. Okay. Could be ordinary point. x naught for a given differential equation. These are the three types you could have. Or it could be a essential singularity. Let me just explain this. So, if p of x as x approaches x naught, the function form of it for your given differential equation, if it becomes infinity, let me say, if it is regular first, okay, it is finite, and q of x as x approaches x naught is finite, that is, it is well behaved, then the point x naught about which you're making the expansion is called ordinary point. Okay, it's the first one. So in this case, x0 is classified as an ordinary point. If on the other hand, like in this case, p of x, if it's just at x equal to 0, it looks like it is going to be, p of x is going to be infinity, right? So if p of x as x approaches, let me write down clearly so that, okay, let me just, so what we're going to say is if p of x as x approaches x naught becomes infinity, either that or both or one of them, question is, can we propose a series solution of that? Okay, may now the solution, can we write such a solution? Is this possible? So this gentleman called Fuchs, what he said was, although p of x and q of x are blowing up, but if the following property is satisfied, said the necessary and sufficient condition for solution, for series solution to exist is the following. Even though they may be blowing up, right? He said, if x minus x naught times p of x this quantity is finite, and x minus x0 whole squared times q of x as x approaches x0 is finite, then still a series solution can be proposed.
So this is an and, right?
What? Yeah, both, yeah. Both have to be satisfied, yeah. If even one of them is not satisfied, you cannot propose it, okay. And this is finite, still a series solution can be proposed. And it's a slightly different form of the power series. This is called ordinary power series. I will talk about that next time, what kind of a series, okay? This is called ordinary power series. In this case, he proposed another series, which is called Frobenius series, okay? That is a solution of the differential equation. It's an infinite series, okay? It is an infinite series, and this is still possible, okay? So that is, we're going to take that. On the other hand, if p of x is, it blows up, like it has an essential singularity, x naught to be essential singularity. If p of x, supposing had a functional form like this, whatever I do, I cannot eliminate the to be something of this nature, right? It's an infinite series like this. If p of x, supposing had it, then if I multiply by x minus x naught, I will have, as x approaches x naught, I cannot get rid of, it's going to blow up. Okay. So in such cases, definitely power series is not possible, series solution is not possible. So basically, we wrote our differential equation in the canonical form so that we can analyze the behavior of p of x and q of x, and accordingly, we'll either propose ordinary power series solution or Frobenius power series solution. If p of x, q of x blows up, but this product is still finite at the expansion point about which you are doing the expansion, most of the time we'll be doing at x equal to 0. This is also satisfied. Both these conditions are satisfied. Then we could still have an infinite series solution as the solution of your differential equation. It's a slightly modified. You need to find under we will talk about that later. Okay, next time. Okay, so it's a slightly modified series. It's called generalized power series solution, and we will discuss that next time. But today we're going to focus on ordinary power series. So, but before that, but still, since we wrote this differential equation, let us just, what is the behavior at x equal to x naught, x equal to 0. Suppose x0 is 0, let us say. What happens? Supposing I decided to do expansion at x equal to x0 equal to 1, okay, what happens? What is the nature of x0? That's the first thing. What is the nature of x0, the point about which you are Can you tell me whether what is what? P of x, for this case, first case 1, let's call that case 1. P of x, for x tending to 0, is what? 0, right? In this case, for Legendre differential equation. P of x is minus 2x over 1 minus x squared. Q of x is L times L plus 1 divided by 1 minus x squared, right? What about Q of x? Is also finite. Right? So what is x0? What is the ordinary point, right? x0 is ordinary point. So we can propose this kind of a solution, right? We can start that as a starting point to get a solution, and then our job would be just to then find out what these coefficients are to get the solution for our differential equation. But if you did x equal to x0 to 1, what happens? So that blows up, right, at x equal to 1. But what about x minus x naught? What about this product? Is this finite or not? Px times x minus x naught. What is the behavior of that? Although that is, not only that, first if that is well behaved, supposing it is infinite, we also have to go ahead and check this second condition also, right? I mean, those are the Fuchs condition. So what is happening to that?
Possible. For the Q things.
P of x is equal at x equal to 1, times the Fuchs condition has been checked, right? So what we're trying to do is x minus 1 times minus 2, this is your P of x, right? 1 plus x, 1 minus x at x equal to 1. There'll be negative sign there, right? So that will cancel, that with the negative sign, and then x equal to 1, so that is 2. So that is, 2, so it is plus 1. So that is finite. This product is finite, right? This condition has been verified, that is finite. What about, not only that we have to verify the other one also, Qx also should not blow up, right? I mean, it should also satisfy that. So you have to check x minus 1 whole square times q of x, which is that, right? L times n plus 1 divided by 1 minus x squared, which is 1 plus x times 1 minus x. How does this quantity behave at x equal to 1? We have to check. Right, which is again, I can put it as 1 minus x whole square, right? So I have a 1 minus x on the top, L times L plus 1, and then in the denominator I will have 1 plus x and x equal to 1, okay? So it is equal to 0. Q of x times x minus x0 square, in this case, is 0. So what can we say about it? P of x equal to 1. I mean, P of x times x minus x0 is 1. This times that is equal to 0. Can we have a series solution or not? If I expand it around x equal to 1, right? I mean, so we have to change the, in the first case it will be, just x to 1. In the other case, x minus 1 took off n, you understand that? And there's a different solution also because it's a generalized power series. Both are finite, right? It is 0, it's not infinity. So we can still propose a series solution about x equal to 1, okay? So this is the analysis you have to do to understand which method should I use. Ordinary power series of, my starting point has to be first decided for a given differential equation. So you first put your, whatever given differential equation, put it in this form, and then look at P of x and Q of x, and then go through this. Is Px at x equal to x0 finite, Q at finite. If it's finite, go with ordinary power series. If it's not finite, and then if it is blowing up, then at least, So what it is what they're saying is the singularity of Px at the most can be as, it can be like, it can be like x minus x naught. That's a large, can decay to that power. Singularity of Q of x can only decay like x minus x naught. Anything, if I had x minus x naught cube kind of a thing, of course we cannot use it, right? I mean, how fast the singularity decays around x naught determines whether a power series solution is possible or not. Okay, so it's just very general principles here. Okay, so this is what is, did I say this is what is a Fuchs condition? I mean, did I write the word? I mean, so that's called, we have to check for this Fuchs condition. If that is satisfied, you know, it's still, although there's singularity at x equal x naught, Fuchs condition is satisfied, we can, we may still be able to at least get one solution through series method. So we will learn how to get, even if I got one solution, how do I get a second solution and all that.
So we would say that that point is a regular point?
Which one?
The,
Yeah, yes, the x0 in the second case is a regular single point, okay? I should also say, it's a singular point but regular. Yeah, maybe we can emphasize the point. It's an ordinary point, regular. It's a singularity that we are able to remove, okay? Maybe some people just say regular point, but it's better to, it's a singularity, it's not an essential singularity, I'm not able to remove it here at all. There is singularity at x equal to x naught, but I'm able to remove it, okay? Yeah, and I'm able to at least give a solution in a certain domain, okay? In this case, in Legendre differential equation, it will be in the, I'll propose a solution in the domain minus 1 x plus 1, okay? In this domain, I'll be able to provide a solution, making that okay. So, any questions here? Yeah,
Did you just choose 0 and 1 randomly, or
there.
for your x, you chose x equals
Okay.
0 and x equals 1?
See, okay. In the second case, you can see that, I mean, I did x equal to 1 mainly because there's a singularity at x equal to 1, right? But if I have ordinary point x equal to, it's easier to first do it because both of them should eventually, whatever method, it should give the same solution, okay? But when you put 0 here, and if it is regular, or if I can find a series solution at x equal to 0, it's better because my series will be so simple that I can convert that into a function or something like that. Because it will become complicated series. And so very rarely I've seen people choosing a different x naught besides x 0 equal to 0. So the first thing we want to test is my solution regular at x 0 equal to 0? Can I make expansion around x 0 equal to 0? That's the first thing we will ask, rather than making it more complicated, okay? But yeah,
what does it mean physically when we have a something which is unsolvable given like a certain position? So like assuming like or is it not possible? Basically what I'm saying is it seems like there is possibility of having something which is solvable everywhere except for one specific point.
no, if once, you know, it is not like you want to solve it in certain domain, let us say. And even if it, you know, yes, you're right. There may be a case where you can solve in the entire domain from minus infinity to plus infinity, okay? That will be the best scenario, okay? But there may be solution cases, differential equation, you can solve it in certain domain only. Like Legendre differential equation will be only in this region, you know, I mean, but that's also fine because if you write this x in terms of cosine theta, it's going to be in the range minus 1 and plus 1, okay? I mean, so you will be solving the differential equation in a certain domain only. As long as, you know, your solution in that domain, fine. But if it is blows up in, you know, whatever region that of interest, then, you know, the method, it is not useful, right? I mean, because it's blowing up, so there's no.
I guess what I'm asking is what does the equation blowing up mean physically?
What did you say?
What does the equation blowing up mean physically?
Not equate, we will see that, okay? Because it'll all depend on the coefficient a sub n, okay? You will see that we will do a problem actually eventually, but the coefficient a0, a1, this is a very general equation, right? It's finding the coefficients we have to determine. If the coefficient a0 is something when we try to determine, that becomes 0 in this. I'm proposing a solution like this. So whatever second order differential equation we have, it'll have two solutions. I have to talk to you about that also. Okay, that solution will be of this form. Okay, let's say I'm expanding around x0 equal to 0, right? N equal to 0. I need to get I need to get these coefficients, okay? So the way we'll do it, supposing I did it like this, I mean, I have to determine all these coefficients somehow to get the solution, right? I mean, that is our goal eventually now. Now, supposing A0 becomes 0, then the whole, the series will not exist, okay? So that would be one scenario that solution does not exist, because it's all embedded on this coefficient A sub n that we are trying to determine, okay? So that is your complete solution. Eventually it is, we know it's a bar series or something like that, okay, that's a very general form. But what is the specific, even each differential equation will have a very specific infinite series, and that infinite series will be determined by the value of these coefficients A0, A1 and A2. So that's where it is embedded, okay? Although they have, we will have a specific example, we'll see what happens, in a given differential equation, why you cannot do the series solution, because automatically, even if you just blindly used it, what will happen is some of these coefficients will blow up and you will not be able to propose a solution of the series, okay? So that you will automatically find also. But they are connected, all these things are connected in some sense, this condition which has been given is embedded somewhere there also, what solution you're going to get it, or proposing, yeah.
Could you explain the difference between the ordinary point, regular single point, and the essential singularity?
Yeah.
Sorry.
You just look at the behavior of Px and Qx at x equal to x naught. And if P of x at x equal to x0, the expansion point of your series, okay, which normally is x equal to 0 normally, okay? If it is finite,
Yes.
it's not infinity, then, and also Q of x at x equal to x naught, both these are satisfied. If both these conditions are satisfied, then x0 is an ordinary point.
Okay.
Okay. This is not satisfied, so, x equal to x naught, P of one of them blows up, okay? Then we go one further step and ask the question, what about this product, x minus x naught times p, is that finite? And x minus x0 squared times qx, is that finite? If this condition is satisfied, then this x0 will be called as regular singular point, because you have singularity, okay? Like in this case, I mean, x equal to 1, there is a singularity or Bessel differential equation, right? Where we saw, yeah. One of them, it will have a singularity, but you're able to remove that singularity by multiplying by x minus x naught. So it has a singularity which decays as you approach x naught, around that point, it decays as 1 minus x naught, okay? I mean, not far, it is not faster than that, okay? So that's what it means, that if you are able to satisfy this condition, x0 will be called as regular singular point. It's not ordinary point, and in that case, you're going to propose a different series solution, which I've not written down, and do it next time, okay? You will, it's a series solution, right? But it's a different type of series solution, okay? That will be proposed. At least we have a series solution as a possibility. But if you had P of x, as I said, like, some weird function like this, right? I cannot remove the singularity at all, right? I mean, Fuchs condition will not be satisfied for that. So for that case, x0 will be called as essential singularity.
Okay.
So is it necessarily guaranteed that if P of x and Q of x are finite, then the Fuchs condition is going to be met? Is it possible that you have P of x, Q of x finite, but then we go to do the Fuchs condition is infinite?
Sorry, I don't understand. If P of x and Q of x is finite at x equal to x0, you have a series solution, which is ordinary power series solution. Okay, you have it, okay? But if it is, blowing up, but at, it satisfies this other condition, subsidiary condition, yet you are able to propose a solution, a different type of solution, part series solution exists. But if I had, if I had my P of X was something like, in P of X, let us say some problem, right? It can, if it is like X squared, I'm not able to, some function that is 2 over X squared or something, if I had something like that. My differential equation is such, I had something like this, I cannot propose a series solution at all because X times 2 over X squared, I still have at X equal to 0, it's going to blow up. So we cannot use this kind of method at all.
I guess I was asking in a logical standpoint, if you have statement A being P of X and Q of X are both finite, and statement B being the Fuchs condition is met, A implies B, but B does not imply A.
I think both of them together are called as Fuchs condition. I mean,
Oh,
the whole, you have, these are just a sufficient condition for a series solution, okay?
Okay.
So, yeah, both of them, these two, I think Fuchs, what he proposed was all of them together, either,
Okay.
this condition or this condition satisfied, we have some kind of series solution for a differential, second order differential equation can be proposed. Okay, that's what it is.
Thank you.
Okay, now, one more thing I want to talk about. So it's a second order differential equation, okay? So whatever it is, it will have two solutions, right? So maybe I should say, I think Fuchs, what he says in the other case, at least one solution can be proposed by a series method. In the other first case, both solutions will come automatically out of the series solution. In this case, you may not get a second linear, you may get one solution. The second solution you get may not be linearly independent. Okay, definitely we are guaranteed of one solution using series method. Okay, that's another thing he says. Okay, that's all right. So this is second order. So our goal is to find two solutions, y1x and y2x, okay, that are linearly independent. So if y1 and y2x are two linearly independent solutions, you can always also have linear combinations of them, which will also be solution, but these are called as complementary functions, complementary solutions. So y1 and y2x are linearly independent solution if, this is an important thing that we'll exploit quite a bit. For y1 and y2 to be linearly independent, this quantity called Wronskian, it will be denoted by the symbol W, which is nothing but determinant of y1 and y2. This is nothing but the first derivative of y1, and this is nothing but first derivative of y2, the second solution. This quantity should not be equal to 0. This condition is satisfied. We will exploit this property, like if my Frobenius series method gives me only one solution, I will use this property to get, even if I get only y1x, I'll use this property to get my second solution. So that way it becomes a very critical thing. And we'll also prove that this Wronskian is also nothing but related to this coefficient p. When you put the equation in canonical form, missed it. We'll prove this in a minute, okay? This Wronskian is also related to this coefficient p of x, and this I will, I'll prove to you in a minute. So, as I said, in general, we may have an inhomogeneous differential equation. So what you do in order to get a solution of a inhomogeneous equation, first you solve a homogeneous differential equation, get the solution. Let's call that as linear combination of y1, y2, something ycx. And then it will have fx under part, which we call this particular solution. It should be chosen such that it satisfies the inhomogeneous differential. That's the crudest way of getting the second solution. But eventually, when you learn the Green's function method, you will not do that. It's just a guess, like the harmonic oscillator thing. We're guessing the solution without knowing the methodology. So if you did not know any methodology, you have to do the crudest way of getting a solution for inhomogeneous differential equation. You first will solve homogeneous differential equation, get y1 and y2, and get a linear combination of that. And to that part, you add certain things such that we know this differential equation, that will be 0. Okay, now you have to find something here that will lead to this right-hand side. So it's just a guesswork, basically. Okay, but that will not always work, and we have to learn proper methods. And the proper method there will be Green's function method. That will be the part of that will be do after the fall break. Okay, Green's function method we'll learn. To solve inhomogeneous differential equation. Right now, we are going to be focusing on different types of second-order differential equation and how to propose the ordinary power series. And if I get one solution, can I use this Wronskian method to propose a second solution? All that. Okay, all that we will do. So that will be our goal right now. Maybe let me just do an example and then maybe talk about the Wronskian method to get the second solution, so you understand what we are trying to do. How to use whatever I've developed so far. So. The solution. I mean, we don't have to do all the stuff, but it's good to illustrate the method through this. So what is P of x in this case? If I have, the whole idea is the differential equation has to be in the canonical form, first step, right? It's already in the canonical form, that can be. So what is P of x?
0.
P of x is 0. Right? And Q of x is 1. Can I propose a series solution? Yes, because because they are finite, so I can propose. So I can, the starting point is this ordinary power series, an x minus x0, I'm going to put that as 0. Expansion point, I'm going to use it as 0 to the power n. Okay, so it's x to the power n basically. X0 has been chosen to be 0. So I can write this as x to the power n. So I'm going to propose this as a general form of the solution. So that's fine. All right. All right, just plug them into the equation and let's see what happens. So y double prime, put all these, substitute all these in the differential equation. So we have a sub n, n minus 1, x to the power n minus 2, n going from 0 to infinity. So that is your y double prime plus yx. So I can write it as an x to the power n. I'm going to just do transformation of variables. I want this to be n, let us say, okay? So that I can compare similar coefficients. So let me just say, if I call n minus 2 as n prime, what will happen is, yeah, n minus 2 is n prime, right? What? All right. So n is n prime plus 2. Okay, let me just see. Okay, so this becomes what? N prime plus 2. N is n prime plus 2 is n prime plus 1, right? This will be n prime. So where n is equal to 0, this is infinite series, so I can have it, let's see here, let me just put it n prime equal to 0 to infinity, equal to 0. N prime plus 2, n prime, sorry, plus an xn, okay. N equal to 0, so it's going to be minus 10. So n prime plus, should I do the other way around? So, sorry, n is equal to 0, so n becomes, sorry, n prime, it starts from n prime plus 2, right? I mean, that's the lowest one. N equal to 0 would be, n, so it starts from n prime plus 2, am I right? Yeah, n prime plus 2. So, to infinity, wherever it is, okay? But it doesn't matter because it's an infinite series, so I really can write this as, something is
So it's n equals 0 and it's n equals n prime plus 2, or n prime is equal to n minus 2.
let us, okay, let us forget about all these things. We can even do it in a different way. Let's not even change the variable, okay? This series start, n equal to 0, this is 0, right? N equal to 1, it is 0, right? So this series starts contributing, that's where it is a problem. This starts from n equal to 2 only, because the coefficients are 0, right, and you're down. That's where. Because when you put n equal to 0, because of that is gone. So really the series is starting from n equal to 2 only, okay? N equal to 1, that's gone. So really it's starting from n equal to 2, okay? That we can do. Now it will be okay. So if I change the variable n minus 2 is equal to n prime, then when n equal to 2, n prime is 0. Okay, so I can now make it correctly. The variables n prime equal to 0 to infinity, n is equal to n prime plus 2, n is equal to n prime plus 2, and this is n prime plus 1, x to the power n prime plus a sub n, x to the power n is equal to 0 to infinity equal to 0. Now it looks good. Okay, so basically we eliminated the first two terms because we're still keeping it n first, and then it is 0, and now I do the change of variables. Okay, then I have both of them. Now since it's a dummy variable, right? N prime or n doesn't matter. Now I can call it as n because it's something which I can change it back to n. After that, so what I have is an plus 2, n plus 2, n plus 1, x to the power n, plus a sub n, x to the power n equal to 0. So one of the things, our goal is to, somehow find out what these coefficients are, okay? Because I'm expanding around x equal to 0, and I have to get these things, okay? At the most, what I've done is, I can perhaps get a relationship between an plus 2 and an, okay? Although I cannot right now still get it directly, but I can get some relationship. If this equation has to be 0 for each power of x to the power 0, x to the power 1, x to the power n, then I must have the following. When you look at the power x to the power n, I must have this relationship satisfied. So compare the coefficient, basically if you're look at the coefficient of the term x to the power n, right? Is this clear? So that gives me some handle on how the coefficients A0, A2 are related, A1 and A3 are related, some idea of that. Okay, so what we have is an plus 2 over, an plus 2 is nothing but negative an over n plus 1 times n plus 2, or we have the following relationship. I think I can get rid of all these things at this point. What I have is an plus 2 over a sub n is nothing but, this is the relationship I have. This is an infinite series that we want to calculate, and I need to somehow estimate these coefficients, but at least I can get the ratio of the coefficients. Now, you can see that if you have something like this, and supposing I took, you know, the following, I say A0 is 1, but A1 equal to 0, I automatically will get one series, because if I put A1 equal to 0, then, you know, A3 and everything will be 0. All the odd coefficient will drop out. And similarly, the other way around, if I put A1 equal to 1 and A0 equal to 0, what will happen is all the even coefficients will drop out. So you have one solution which has got only odd powers x, other one is even power x, so they're already linearly independent. Okay? So that's how you will solve, in this case when it's an ordinary power series solution, you can do it that way. So what do you have? A2 or A0, n equal to 0. You have 1 over, this is 1 over 2, which I can write as 1 over 2 factorial. Okay. A4, you have the ratios like this. So I can write it as A4 over, what is it? I have A4 over A, the coefficient n equal to 2. Right, A4 over A2 I can get. A4 over A2 is n equal to 2 is 3 times 4, right? So this coefficient for n equal to 2, what you get is A4 over A2. And so if I take A0 out, what will happen is because of this relationship, if I put A1 equal to 0, all others, I'll just, A3 will be 0. Because of that, A5 will be 0 and everything. All I have to find is the following. This is 1 plus A2 over A0 x squared. The next coefficient will be A4 x to the power 4. And so on and so forth. Okay. So what I have is that the first solution will be obtained using this condition, and second solution y2x will be obtained through that. So let me now say y1x is nothing but A0. What is A2 over A0 is minus x squared over 2 factorial. A4, I need A4 or A0. What I have is A4 or A2. So I can calculate that because I need A4 or A0, which is nothing but A4 over A2 times A2 over A0, multiply that. So that is nothing but 1 over 4 factorial. So this coefficient is nothing but 1 over, it changes sign. Right. Is this clear? Times 3 times 2, and the negative signs will cancel, so A4, A0 is that. So the recursion relationship gives you A4, A2, but what we need to get the solution is A4 over A0, which can be calculated. Now, and we can, constant time solution is solution, I can take as 1 or whatever it is, doesn't matter. So do you know what this series is? The infinite series, can you relate that to a function? Or let's first if you want to write it in compact summation notation, what will you write it as? So here you can choose now A0 equal to 1, doesn't matter, because constant time solution will always be a solution, it could be anything. If I want to write it in a compact notation. Sign is changing, right? Positive and negative. So negative, can I have that? And then, or it's like x squared, x to the power 4. Can I write it like this? And n going from 0 to infinity. Then here, n equal to 0, 0 factor is 1.
Yeah.
N equal to 1, 2n. Can I put it like this? So that if you don't know the functional form, at least write it in a compact notation, this infinite series, okay? But this is a series that you know. It's an even function in x, and at x equal to 0 it is 1. Do you know any function that behaves like that? Hmm?
Oh, x equals 0 to 1 sine. Cosine.
Cosine x. So that's cosine of x. Okay, so this we know because that is, after all, this is your harmonic oscillator solution. One has to be cosine of x, right? I mean, but we have just proven that methodology works. Whatever we pulled out our head, the series solution, it gives you that solution, right? I mean, so this is nothing but cosine of x. You want from series to, you should always be learning how to go from series to solution, series to function, function to series, right? I mean, some of the common ones, sine, cosine, exponential, natural log of 1 plus x, those are the things that you need to know, how to go back between series and function to solve it in some of these problems. So what is the second solution now? Can you do the second solution? Based on from here as a series solution, I know you can get that. y2x, we are going to do it. You go back to here. Now we are going to put a0 equal to 0. So that means a2, a4 and all will be 0, right? So a0 equal to 0 implies all of the coefficients, even coefficients, will be 0 based on this regression relation. This is what they call as a regression relationship. So for each of these differential equations, our goal is to first get this recursion relationship, and then we try to get the solution. Okay. So y2x is what? I'm going to put a1 equal to 1 in this case. So I'm going to take out a1 out first. It starts with x. The next coefficient I have to determine is a3 over a1 times x cubed, right? a5 over n x power 5. This is an infinite series, all these coefficients. If you can get a few coefficients, you may be able to identify the series, or you can write it, or guess the function. So what is a3 over a1? a3 over a1, we're going to put n equal to 1, right? N equal to 1, minus 1 plus, so it's like, looks like a 3 factorial. Okay, then the next one is, I will get n equal to, I need a5 over a3 I'll get, I think. So n equal to 1 is giving me that, right? So here n equal to 3 will give you minus 3 plus 1 is 4, 3 plus 2 is 5, right? So, and our goal is to get a5 over a1. Right, a5 over a1 is nothing but a5 over a3 times a3 over a1. So that is nothing but 1 over 5 factorial. So what you have is a1 x minus x cubed over 3 factorial. And this will become plus, right? a5 over a1 is x power 5 over 5 factorial. All right, this is an oscillating series too. And if you want to write it in a compact notation as a series one, how do you write it? sign is changing, right? So I need to have something of this nature, definitely. And next part, 2n plus 1 divided by 2n plus 1 factorial, will it satisfy? Okay, so that is what you have there, and here this is what you have, and this is nothing but your sin x term, because sin x at x equal to 0 is 0, so you know that it will happen, and it's an odd function, right? Change the sign, so that is your sine function. So are these linearly independent solutions? I will use check. So we got two solutions from power series method. Are these linearly independent solutions? What did I say we have to check for linear in the beginning of the lecture? Must be not equal to 0, right? So the Wronskian in this case is y1x, one of the solutions, let's say, but it doesn't matter which one, we call it sin x, cosine x, right? You have to take the derivative of this, which is sin of x, y1 prime x, minus sin of x. We have to check whether it is not equal to 0. So that is nothing but minus sine square x minus cosine square x, okay, which is equal to minus 1, which is not equal to 0. So the solutions that you found out are linearly independent. Okay? How much time do I have?
1 minute over, actually.
Oh, so I will not talk about that. Okay, so maybe it's better to do the other one next time, because because I want to use the Wronskian method. This is the property, but I'm going to exploit that to get the second solution, right? I mean, I'll get y1x, okay? And I will use the Wronskian. That's just because I know I'll construct a second solution based on the property, based on this determinant that we have written to construct the second solution. And you can see why I may have a formula, but it will not be useful until I do something, because if I don't know the solution, why did I give the formula in terms of Wronskian in terms of P? I gave it because, I mean, if I'm going to use a method to get second solution, how can I, calculate this indeterminate? I cannot calculate the indeterminate, right? But I know the differential equation, so I know how to calculate, identify P of x. I can calculate W of x through that. I mean, through that formula, I can calculate easily, right? I mean, even though I don't know the second solution. So once I have the Wronskian, I will give you a formula in terms of y2 and y1, how they are related. Okay, so it's something, I'm not writing full formula, but it is. We prove this, okay? I mean, you know the Wronskian, given the differential equation, you can always calculate the Wronskian. So you will know this. And you calculate, let's say, the one solution using the series method, okay? So once you have that, all you have to do is integrate this to get your second solution. So that's useful because when we consider examples where, P of x is, blows up, but x minus x naught times P of x is finite, there may be situation, only one solution will come out of series method, okay? The second solution will not be linearly independent. So I had to find a second linearly independent solution, and I'll use this methodology, just basically exploit this property to get this formula, and then we'll use that. And this is why, in order to use this formula, the other thing you have to learn is, if you leave it in an infinite series form, it's useless because I cannot integrate. I have to understand how to convert always a series into a function. Then I can do the integration easily. So that's why you should learn how to go back and forth between a function to series to function. At least for common series, right? I mean, it's not always possible, but some of them you can. Then this method is useful. But if you are not able to identify corresponding to some series, infinite series, a function, then again, this is useless, this method, because how am I going to integrate that, right? So we have all, different tricks depending on the problem at hand. Okay, so we'll continue next time from this and then talk to the Frobenius method. So that will be many of the class of second order differential equation fall under that category. So we have to learn that before we go to specific physics problems. All right, let's stop here.